Welcome to the debate. Today we are wading deep into C++ territory. We're tackling a really foundational design choice, one that, well, completely upended by C++11 and then C++17. How we pass non-trivial objects into functions.
Right. We're talking about that long-standing best practice, maybe even dogma for some, of using const tn, a constant reference, versus the modern way, which is often more efficient, of just passing by value, just t.
Exactly. That old gospel, as you put it, of defaulting to const tn. I mean, it was there for very good reasons, right? To prevent unnecessary, often really expensive deep copies of large things like standard containers or strings.
Absolutely. You didn't want to copy a huge vector just to look at one element. But you're spot on. Move semantics, and especially guaranteed copy elision, they've entirely rewritten the performance handbook here.
The rise of R values and, crucially, that mandatory copy elision for temporaries in C++17, it means that let's say, the safest and most performant way to handle an argument has fundamentally shifted, particularly for functions that, intend to take ownership or store the argument. We often call these sync functions.
And well, that sets up our core disagreement for today, doesn't it? Does the efficiency offered by this modern pass-by-value pattern, the T approach, does it essentially render the traditional const tn idiom obsolete, at least for these consuming sync functions? Or does const tn still have an irreplaceable semantic, maybe even performance advantage sometimes? That means we need to keep let's say, a highly nuanced, intent-driven approach.
Okay, so I'll be arguing that for any function that really acts as a sink, the modern pass-by-value pattern, T, should probably be our new default. It's a, it's a unified, clean API, and it maximizes efficiency by leveraging these modern language features to give us the single best path for both L values and R values.
And I'll be arguing that, well, const tn remains absolutely critical, maybe even the gold standard for observer functions, those that just need to read the data without taking ownership. And its real strength lies in its conceptual clarity, its communication of intent, and that guaranteed zero copy overhead for just reading. Which means, yes, the framework has to remain nuanced and very contextual.
All right, let's kick off with those sync functions then. For an object that must be stored internally, think about setting a class member like a cdar string or something. The pass-by-value idiom, T, I argue is now superior. Before C++11, we often had to write two separate overloads, right? One taking const T and another taking T and, the R value reference, just to handle both named objects and temporaries efficiently.
Oh, I agree. That complexity was definitely a burden. Maintaining those two overloads, yeah, it was boilerplate, easy to get wrong.
Exactly. And the beauty, I think, of the single pass-by-value signature T is that it kind of delegates the efficiency decision. It pushes it to the caller and the compiler. But the real game changer, the kicker, is in the R value case, like passing a temporary string that you create right there in the function call.
Right, you're talking about the guaranteed copy elision for pry values here. That's C++17 specifically. Maybe walk us through the practical optimization there, because, guaranteed copy elision for pry values can be a bit of a mouthful.
Yeah, fair point. Absolutely. So when you pass a temporary, what the standard calls a pry value, or pure R value, to a function taking its parameter by value T, C++17 guarantees something pretty remarkable. The compiler must construct that temporary object directly into the storage allocated for the function parameter on the stack. There's no intermediate copy, no intermediate move construction to get it into the parameter variable. It's just dot, constructed right there.
So the parameter itself is the temporary object, essentially.
In effect, yes. The total cost for the parameter's construction is just that single initial construction of the temporary. Then, inside the function, you typically just perform one final, usually very cheap, move assignment into your class member variable. In that sequence, one construction, one move assignment is exceptionally efficient. That's what really cements T, in my view, as the optimal choice for consuming temporary values.
Okay, that is a compelling argument for the R value optimization. It's undeniably a massive win for modern C++. But we have to look at the whole picture, right? The const T and idiom, it's still the clearest way to express intent when you're just inspecting data. It remains the gold standard for those observer functions.
Well, sure, but that focuses only on the observer role, which is, orthogonal to the sync role, where consumption, taking ownership, is mandatory.
It is orthogonal, but the contrast highlights exactly where we must retain nuance. Passing by const reference communicates a very clear, almost ironclad contract. This function is non-owning, it's read-only. It promises not to mutate the caller's object. That immediately enhances code safety, readability, and crucially, it guarantees zero copy overhead right at the function call boundary itself.
Okay.
It costs absolutely nothing to cross that function call boundary and just start reading the data. Const tn is really the canonical C++ expression for borrowing data.
All right, let's pivot then to what I think is probably the biggest remaining area of doubt for developers who are maybe transitioning to this T pattern, the L-value case. You correctly noted that when we're dealing with a persistent named object and L-value, the pass-by-value sync approach does mandate a copy construction just to create the local parameter, and then it's followed by a move assignment into the member variable.
And that's really the crux of my concern about just adopting T as a sort of universal default for syncs. You're forcing two distinct resource management steps, a copy construction, then a move assignment. The traditional const tn sync setter, by contrast, it takes the reference and then performs just one explicit deep copy assignment inside its body. Is that inherent complexity, forcing that intermediate copy construction of the parameter, is it really worth it?
I'd argue yes, the complexity is manageable, and the performance profile is actually often superior even for L values. That mandatory copy construction of the parameter, okay, it might seem like a heavy lift up front, but let's compare the subsequent operations. In the traditional const tn sync, that single operation you perform, the deep copy assignment into the member, involves several potentially expensive steps, right? You might check for self-assignment, you have to deallocate the existing heap memory, allocate new heap memory, and then do a deep byte-by-byte copy of the actual data.
An expensive operation, yes, particularly for large objects. No argument there.
Okay, now look at the modern T-sync again. We have that one initial copy construction for the local parameter. Fine. But the second step, the move assignment from that local parameter into the member variable, that's typically exceptionally cheap. For types like std.string or std.vector, it's often just copying, 3 internal pointers and maybe size capacity metadata. It usually costs less than a dozen CPU instructions. So we're trading the old model's guaranteed expensive deep copy assignment for a mandatory initial copy followed by a single very cheap pointer swapping move. The overall cost profile can actually be better, even for L values sometimes, and dramatically better for R values due to elision.
That's a persuasive analysis, I'll grant you, especially for standard library types like containers, where moves are designed to be cheap. And I concede that the cost profile heavily favors a cheap move operation over a full deep copy assignment. But this whole argument hinges entirely on the move operation being genuinely cheap, right? If the T-sync pattern is so robust, why don't we see it just completely replacing const tn everywhere? It's because, I think, the reference approach brings certain guarantees, particularly around optimization and visibility, that the value approach just can't match in all scenarios.
That's an interesting point. But I think we actually need to challenge the perception that const tn is somehow a zero-cost abstraction. It isn't really. It introduces indirection, fundamentally. It's implemented as a pointer, under the hood, to some external memory. And more critically, that indirection can sometimes cripple compiler optimization efforts.
Sorry, I don't really buy that the optimization penalty is significant enough to outweigh the semantic benefits and the boundary crossing efficiency of const tn in, general application programming. Let me explain why I think that.
Okay. When the compiler encounters a const tn parameter, it often can't guarantee that the value being referenced hasn't been changed by some other means, maybe an aliased pointer elsewhere, a signal handler, another thread modifying it concurrently. This whole aliasing concern forces the compiler to generate conservative code. Instead of trusting that the data is stable and maybe caching it in a fast CPU register, the compiler might be forced to repeatedly reload the value from memory, perhaps across function calls or inside loops. This kind of register thrashing can introduce subtle performance penalties, especially in tight inner loops.
Look, I acknowledge that aliasing issues are a real technical constraint for compilers. Fine. If you're writing, I don't know, a high-performance numerical library, like a linear algebra engine, or maybe a graphics shader, where you're looping thousands of times over the same data and locality is absolutely paramount, then yes, okay. Passing by value might give the compiler the visibility it needs for really aggressive optimizations, maybe even SIMD vectorization.
Precisely, a value parameter is a local object. Its lifetime and scope are fully visible to the compiler within that function, allowing for those aggressive optimizations. The reference is, well, opaque.
However, for the vast majority of application code, general API calls, passing complex domain objects around, using standard containers in typical ways, the performance penalty of maybe an extra dereference or some conservative aliasing assumptions is likely negligible, tiny. And it's almost certainly outweighed by the semantic clarity of the Const TN contract and the sheer cost saving of avoiding a potentially huge copy construction just to read some data from a large structure. We shouldn't compromise a clear code contract for an optimization that's realistically only relevant in pretty extreme, highly localized performance-critical code segments.
I might frame it differently, though. The T approach removes a potential optimization roadblock entirely. It shifts the burden back to the compiler, where maybe it belongs. By using const T and end, you could argue we're effectively telling the compiler, hey, don't trust this data too much, which inherently limits its ability to optimize aggressively.
Or perhaps we're telling the compiler, hey, don't copy this potentially huge thing, which is often a far, far greater performance gain for large objects.
And let's shift gears slightly and talk about type characteristics and safety, because this is where the value of const Tn becomes, I think, undeniable, and where a default T approach just fails immediately. I'm coming at this from a safety perspective now.
Okay, go on.
For polymorphic objects, classes designed to be used through base class pointers or references, using pass-by-value T is almost always a catastrophic bug. It leads directly to object slicing.
Right.
All the derived class behavior, the vtable pointer gets messed up, derived class data members are just lopped off, you lose the object's true identity. This absolutely forces us to use const base and, or perhaps smart pointers. So T pass by value is basically a non-starter for polymorphism.
You are absolutely correct. Const Tn, or a reference to the base class, const base n, must be used for polymorphic types to maintain correct runtime behavior. That has to be like an unshakable rule in any reasonable C++ parameter passing framework. We're really focusing the debate here on non-polymorphic but potentially expensive to copy types like the standard containers, where move semantics are effective and designed to be cheap.
Okay, but even within those non-polymorphic types, the calculation isn't always straightforward. What about non-trivial types where the move operation itself is nearly as expensive as a copy? Maybe due to, let's say, suboptimal class design, where internal resources still have to be copied during a move. In those cases, the modern T-sync pattern loses its main performance advantage, doesn't it? In those sort of edge cases, the const T and approach, followed by an explicit copy inside the function if it's actually needed, might remain the safest default. It doesn't incur that mandatory copy cost up front, unless you absolutely determine you need it.
That's a valid limitation, yes. It means we might need to profile types where we suspect moves are unusually expensive. But let's define the other boundary of this framework, the cheaply copied types. This is where const Tn is, I think, undeniably the wrong choice most of the time.
Agreed. There's definitely a lower bound where copying is better.
For truly cheap to copy types like the fundamental primitives, int, float, double, pointers, or small structs that basically fit within one or two CPU registers, pass by value T is almost always the recommendation. and that's regardless of whether it's a sync or an observer function.
Right. In those cases, the overhead of setting up the indirection for a reference, plus those potential aliasing concerns we discussed earlier, probably outweighs the absolutely minimal cost of just copying the value itself. A cheap copy is better than cheap indirection in that context.
And this, I think, supports the notion that the domain where Const Tn is the optimal choice is becoming increasingly narrow in modern C++. It seems confined almost entirely to really two key roles: being the only safe option for polymorphic types and being the preferred choice for observing large, non-polymorphic parameters where you don't want to copy.
For consumption, for syncs, T is generally better now. For cheap types, T is always better.
Well, I see that narrowing not as a sign of obsolescence, but perhaps as the sign of refinement. It means a developer now has to adopt a more systematic, intent-driven decision process. We have to move away from just defaulting to one thing without thinking. If Const Tn is clearly best for the crucial observer role, and it's the only safe way for polymorphism, its domain has simply been, well, redefined and clarified by modern C++. It hasn't disappeared. So the overall picture, I think, shows that modern C++ really forces us to discard that old universal, always default to const reference mentality. The power of guaranteed copy elision combined with efficient move semantics means that for functions with that clear sync intent, T provides a unified, highly efficient path. And by embracing this, we really harness the full optimization potential of the modern language and standard library, leading to performance gains, especially for R values that are substantial and predictable.
And while your analysis is compelling regarding the superior performance of the T-sync pattern, particularly for R values, we absolutely must prioritize the code contract, the clarity, the safety, where consumption isn't actually necessary. Const T and perfectly expresses that borrowing semantic. It provides safety and essentially zero-cost clarity for observer functions where no copy is needed or wanted. This complexity just means we need multiple perspectives. The choice remains fundamentally driven by semantic intent. Is this function an observer, or is it a sync?
The intent dictates the parameter type. It's about using the most effective tool for the specific job at hand.
Precisely. The optimal strategy is determined by the function's precise role and the characteristics of the type being passed. This results in a necessary, context-dependent framework, not just a new universal rule replacing the old one. Developers now need to be educated, really, to choose consciously from all three essential tools in the toolbox. T, passed by value, const T, passed by const reference, and sometimes even T and O directly passed by R value reference, mainly for perfect forwarding scenarios. It's a more nuanced world now.